I'm Castrense Savojardo from Biocomputing Group, Department of Pharmacy and Biotechnology, University of Bologna in Italy. In this poster presentation, entitled Bologna Biocomputing Pipeline, combining multiple tools for protein functional annotation in kappa, we present the collection of tools and resources we connected into a pipeline for protein functional annotation in the context of the last edition of the critical assessment of functional annotation, which is currently still ongoing. Our pipeline integrates different resources and tools performing functional annotation using complementary approaches, including transfer by sequence similarity, guilty by association using protein-protein interaction data, and machine learning-based approaches. So, transfer by similarity is carried out using the Bologna annotation resource, version 3, bar 3, which is our primary tool for protein functional annotation. So briefly, bar is based on a pre-computed clusterization at 40% sequence identity and 90% of coverage of all the protein sequences in the UniProt-KB database, and subsequent transfer of functional annotations that are enriched within each cluster. Enrichment is performed using a stringent statistical procedure based on exact Fisher test and Monferroni correction. So new sequences that are not present in the bar database are firstly mapped into a cluster by alignment and then annotated with statistically validated annotations that are found in that cluster. Here we perform an update of bar 3 using the most recent annotations from the gene ontology annotation database, which allow to extend and refine the set of statistically validated terms that can be transferred to new sequences. On the other hand, we perform guilty by association using protein-protein interaction data and the NetGA Plus tool, which is a tool we recently developed for network-based functional enrichment. So briefly, NetGA internally computes the so-called Go-specific functional modules that are basically subnetworks of the string interaction network built starting from proteins sharing the same Go term, referred to as seed nodes, and also including the minimum number of nodes lying in shortest paths between seeds, referred to as connecting nodes. So here a new protein is annotated with a specific Go term if it enters the Go specific functional module either as a seed or a connecting node. So in this way we are able to transfer functional information from seed nodes to connecting ones. So finally, the above methods were complemented using BUSCA pipeline itself we developed for prediction of the protein cellular component. So BUSCA internally integrates several different tools based on machine and deep learning approaches that are organized into kingdom-specific workflows. So overall, BUSCA allows to predict up to 16 different compartments for an input protein sequence. So the predictions and annotations obtained with the three different approaches were combined together into a consensus annotation by merging them into a single coherent functional annotation. And predictions scores were computed using a simple scheme taking into consideration the Go information content, which is directly related to the observed frequency of each Go term in an external database. So here we assign to each Go annotation a score which is inverse proportional to its information content. And the rationale behind this choice is to have lower scores for those Go terms that are expected to be less frequent and hence less probable to be assigned. I'm Castrense Savojardo from Biocomputing Group, We evaluated our pipeline using two different datasets. The first one has been generated to reproduce in-house a kappa-like benchmark using Goa releases from August 2017 and December 2019 and computing the Go annotations that have been acquired in this time lapse. So we use these specific releases in order to ensure that we have no overlap with any training data used for training our methods. We also perform self-assessment in terms of coverage using the official kappa-4 targets. Results of the kappa-like benchmark are shown in this table, in which we report prediction performance and coverage as a function of the combination of the different tools in our pipeline. As you can see, the combination strategy seems to be effective for improving the F1 max score on all the three ontologies. And in particular, performance on cellular component ontology is quite good. It's very close to the one achieved by top performing methods in the previous edition of kappa. The improvement seems to be related to the increase of the prediction coverage. And this increase is evident also when we evaluate the coverage on the official kappa targets. Using the full pipeline, so combining different tools that are complementary in the predictions they provide, we are able to achieve up to 84% of coverage for bioprocess, 82% for molecular function, and 100% for cellular component. So we expect the pipeline to be effective also in this kappa-4 benchmark. That's all. Thanks all the people contributing to this work, and of course you for your kind attention. Thank you very much.